Good morning and welcome to the last Algebra I lesson of this school year. For those tuning in for the first and last time, my name is David Dye. I am currently in my third year of teaching and second year at Algebra I High School, and this semester I am teaching algebraic connections and discrete math. So the last couple of weeks our focus has been looking at quadratic functions, their transformations, looking at exponents and their properties. And so this week we're going to take a look at the future, what you're going to be seeing in geometry. And so we're going to spend today's lesson looking at 3D solids and really focusing our attention on how we can use our algebra skills in order to make sense of geometric relationships as we're describing these 3D solids. So the learning goal today, as is for most of our learning goals, is we're going to look for patterns and then we're going to develop these algebraic models that describe the geometric relationships that we see. So how can we use the algebra skills that we've developed in order to look ahead and kind of make sense of some of the geometric relationships that we're looking at? Now, the agenda to accomplish this. I'm going to introduce you to some common language with some vocabulary. So we're going to try and establish a baseline for that. And then we're going to take a look at a task called the painted cube. And then from there, I'll talk more about your chance to win a prize since you're tuning in to watch this lesson today. Now, what I want to begin with is just talking about some common cubes. So at home you might have the storage cube or storage bin unit kind of thing where you've got toys or other household items in the storage cube. Another common cube that you might come across in board games are dice. And I've got this blue styrofoam die that I'm showing you. And then I think something that we're all fairly familiar with is this idea of a Rubik's Cube and this toy. And so what I really want to focus our attention on is, to establish this commonality between these cubes and their features. We want to establish some vocabulary. So as we're thinking about these cubes and their structure, I want to give names to these features. And if you have a cube at home that is readily available, grab one. If not, more than welcome to continue to look on the screen or what I have in my hand. But what we see here, these flat surfaces on the cubes, we're going to call a face. Okay, and these vocabulary terms are going to come up as we continue to discuss the painted cube task. So the flat surfaces, we're going to call a face. The edges are where the faces meet. So on a cube, we've got these 6 faces. We've got these 12 edges that are on a cube. And then where the edges and faces come together, we're going to call vertices, or you could think of them as the corners on our cube. Now, with the painted cube task, we're going to be looking at structures that are a lot like the Rubik's Cube that you see here in how it's partitioned into these smaller cubes. And so the task has us kind of making sense of this particular situation. In case 1, you're looking at the small unit cube that you see here. And if I'm looking at a Rubik's Cube, it's going to be one of these small individual cubes on the larger Rubik's Cube itself. In a 4x4 case, what we're looking at is a cube larger than this Rubik's Cube that is 4 across, 4 in height, and then 4 in its depth. And what I want you to understand is in this particular task, we're imagining that we're painting this 4x4x4 cube on all of its faces. So all of these surfaces are covered in paint. And I want to know, if I'm covering this entire thing in paint, is how many of these smaller unit cubes, these 1x1 cubes, will have 3 faces painted, how many are going to have just 2 faces painted, how many will have only 1 face painted, and then how many are going to have no faces painted at all. And once we've assessed all of this for case 4, how can we then determine the answer to these questions for a cube of any size, if it is case 2, case 3, or beyond? And so when we're looking at case 4, here's an image of a cube that is 4x4x4, entirely covered in paint. And now what I'm going to show you are the locations of where the individual cubes that have 3 faces painted, 2 faces painted, and 1 face painted, as well as no faces painted, are located in our larger cube. So I really want you paying attention to the location and thinking about some of the vocabulary that we established previously. This term of face, edge, vertex. And so here is where all of the smaller unit cubes that have 3 faces painted are located. Here are the locations for our unit cubes that have 2 faces painted, the location of our unit cubes that have just 1 face painted. And when I remove all of the cubes that have paint on them, here's what we're left with that have no paint on the cubes at all. And again, I want you paying very specific attention to the location of where each of the 3 faces painted, 2 faces painted, and 1 face painted are located on our larger cube. And let's try and figure out how many these are. So when I'm looking at 3 faces painted, here we're going to have 8 of these smaller cubes with 3 faces painted. And if you have a cube at home, thinking about these locations, what we see is that the 3 faces painted are going to be the corners or the vertices of our larger cube. So there are 8 of those. When I'm looking at the cubes who have just 2 faces painted, what we see here is that they're occurring along the edge of our cubes. And we're not including the corners because we've already counted those as 3 faces painted, so we remove the corners, and everything else that's along the edge has just 2 faces painted. Additionally, we have 12 edges. So in this particular case, for a 4x4x4 scenario, I've got 12 times 2, which gives us 24 total cubes. When I'm looking at the situation that has just 1 face painted, I remove the corners, I remove the edges, and I'm looking at the square in the middle of each face. And we established earlier that on a cube, we've got 6 of these faces, 6 surfaces. And so in this particular case, I've got a square that has 4 unit cubes. So 4 times 6 is going to give us 24 total cubes that has just 1 face painted. And then when I remove all of these unit cubes that have paint on them somewhere, at the very center of this larger 4x4x4 is a smaller cube that is of 2x2x2 dimension. Okay, and there are 8 of those. So we've kind of answered that first question that I posed in terms of how many of each of these cubes have 3 faces painted, 2 faces painted, 1 face painted, and none. But now I want us to think about in any particular case scenario, any size cube, right? And for us to really make sense of this and adding to the vocabulary that we have, I want you to think of all of the situations where the cubes have paint on them. We're going to define that as surface area. So how much of the surface of our larger cube is being covered in paint? And then when we're looking at how many total cubes we're dealing with, we're talking about this idea of volume. So additional vocabulary, when we're talking about 3D solids, if I'm covering the entire figure, we're calling that surface area, and then the entire total number of smaller cubes in this case, so how much space we have, is going to be called the volume. So what I want to do now is kind of transition and look at case 2 and case 3, try and make sense of how many of these cubes have 3 faces painted, 2 faces painted, 1 face painted, and none, and then see if we can't use that information to generalize and talk about any size cube. So when we're talking about a 2x2x2 cube, here we have 8 total cubes, and if I cover that entire thing in paint, all 8 of the cubes in that size are going to have 3 faces, 1, 2, 3, that are covered in paint. When I'm looking at a 3x3x3 case, so if I were to cover an entire Rubik's Cube in blue paint, what we see is that there are 8 cubes with 3 faces painted. And again, pay attention to the location. In that 4x4x4 case, we were looking at the corners. In the 3x3x3 case, still looking at the corners. When I'm looking for just 2 faces painted, when I remove the corners, we're looking again at the edges. And here I've only got 1 cube along this edge, but since I have 12 edges, there are 12 cubes with 2 faces painted on them. When I remove those corners and I remove the edge pieces, I'm left with this very center square. And so with 6 faces on a cube, I'm going to have 6 of these smaller cubes with 1 face painted. And then when I remove all of the smaller unit cubes that have paint on them, we can see that I've got 1 cube in the very center that has no faces painted at all. Now, how can we use this information for case 2, for case 3, case 4 on the previous screen in order to make sense of any size cube? Well, let's organize it into a table. In case 1, that very first image that I showed you, all I have is just one cube. And if I cover the entire thing in paint, all 6 faces are covered, and so these are going to be 0 when we're completing this table. When I'm looking at that 2 by 2 by 2 case, on that previous screen, we have 8 total cubes. And if I covered that entire 2 by 2 by 2 cube in paint, all 8 of these smaller cubes have 3 faces painted. And so in this particular situation, you're going to have 0 cubes with 2 faces painted, 1 face painted, and 0 faces painted. In the 3 by 3 by 3 case, we've got 27 total. We've already described how many have 3 faces painted. Again, think about what we might be seeing in terms of patterns. We've got 12 cubes that have 2 faces painted, 6 that has 1 face painted. And then when I'm looking at the 4 by 4 case, 64 total cubes here. Again, I've got 8 cubes that have 3 faces painted, 24 cubes that have 2 faces painted along those edges, 24 in the middle of each face, and then 8 in the very center of my 4 by 4 by 4 case. Now, I want us to kind of look at the numbers that we see here and see if we can establish any kind of trend that we might be able to use in order to make sense of the 5 by 5 by 5 case. Right? Can we make a projection into the next situation, and then can we use patterns from there to generalize to a cube of any size? Now, what you might notice for the total number of cubes is that if I multiply across in my dimensions, 1 times 1 times 1, I get 1 cube. 2 times 2 is 4, times 2 again gives me 8. 3 times 3 is 9, times 3 is 27. Same here, if I multiply 4 times 4 times 4, it'll give me 64. So if I'm looking for the total number of cubes in a 5 by 5 by 5 cube, what we see is we have 125 total cubes. If I'm looking for the pattern across the 3 faces painted, I want you again paying attention or recalling the location of where those were. And if you remember, in the 3 by 3 by 3 and the 4 by 4 by 4 cases, those 8 cubes were the corners or the vertices of the larger cube we were looking at. And that's pretty constant, which means if I made this cube larger, I still only have 8 vertices and still only have 8 cubes with 3 faces painted. When I'm looking at just 2 faces painted, recall that these were along the edges. And if I'm looking at a cube, we have 12 of these edges. And so if I've got these 12 edges and I'm taking away the 2 corners on a 5 by 5 by 5, 5 subtract 2 gives us 3. So 3 cubes along these 12 edges, I've got 36 total cubes that have 2 faces painted. If I'm looking at 1 face painted on a 5 by 5 by 5, that's the very center square on each face. And in this particular case with the 5 by 5 by 5, that center square has dimensions of a 3 by 3. So I've got 9 total cubes on 1 face, and a cube has 6 faces, so 9 times 6 gives us 54 total unit cubes that have just 1 face painted. And then when I remove all of the cubes that have face on them, or paint on them, rather, then I'm left with a 3 by 3 by 3 cube in the very center that has no faces painted at all. Now, how can we establish any kind of pattern for any size cube? Let's think about the total number of cubes here. If I'm just multiplying across to get the total number of cubes, we could think of this 1 as being equal to 1 to the 3rd power. This 8 as 2 to the 3rd power. This 27 as 3 to the 3rd power, and so on. And so when I'm thinking about the total number of cubes for any size cube, that's just its size to the 3rd power. And this is, for a cube, the equation or the expression that models volume. Right? So we're looking for patterns and we're establishing how we can come up with these equations or expressions that model geometric relationships. If I'm looking at the three faces painted, think again about the location. When I'm looking at these cubes, all of these that have three faces painted are the corners. And the number of corners on a cube does not change regardless of size. We're always going to have 8 corners, 8 vertices, which means on any size cube, we're always going to have 8 smaller cubes with 3 faces painted on them. Here, when we're talking about the 2 faces painted, recall that all of those occur along the edges. And I have 12 edges on a cube, which means my expression modeling this number of edges is going to be 12 times n minus 2. That minus 2 referring to the 2 corners along each edge that I would subtract. When I'm looking at one face painted, we've already accounted for the corners and vertices. We've already accounted for the edges. Recall that the one face painted is always the center square on each face. And because I have 6 faces, and I'm talking about the center square, the expression that we come up with is 6 times n minus 2 squared. And then when I remove all of those cubes that have paint on them, and I'm looking at the very inner part of our larger cube, that's going to be the smaller cube of dimension n minus 2 to the 3rd power. Now, from an algebraic perspective, so the stuff that we've talked about on TV and throughout your semester so far, we can graph these things. I can graph f of x is equal to 8 and have this constant function. I can graph 12 times n minus 2 and I can graph this linear function, this increasing line. And here I'm modeling the number of corners, and look at how it's staying constant. It doesn't change. It's always going to be 8. Whereas if I change the case number I'm looking at, if I go from 5 to 10 to 15, the number of edge cubes that have 2 faces painted is always going to go up. In blue here, we're talking about the face cubes, the center square on each face. And we just finished talking about quadratic functions, so look at the shape of this graph. It's that parabola, and we can model that with 6 times n minus 2 squared. Additionally, when I'm talking about the inner cube, we can model that, n minus 2 cubed, and when we graph it, we end up with something called a cubic function, something that you're going to explore more in Algebra 2. But again, these are all algebraic perspectives, the stuff that we've talked about before. To make sense of the geometric perspective, we have to make sense of the expressions themselves. We've got to understand where the numbers are coming from. And so the 8s we've talked about before as representing the corners or the vertices on our cube, and it's always going to be constant. It's always going to be 8 for a cube because that doesn't change. But when we're talking about this expression of 12 times n minus 2, the n minus 2 part, what we see in parentheses, represents our case number minus the 2 corners along each of the 12 edges. So that 12 represents the number of edges on a cube. Okay, and so it's important in this particular case that's different from the algebraic perspective of just creating the model and graphing it to make predictions. We want to make sense of each of these parts geometrically. For our expression here, for that inner square, the n minus 2 squared part represents the case number minus our 2 edges on either side, giving us the inner square, and a cube has these 6 faces. So that's making sense of that particular expression. And then lastly, this n minus 2 cubed, that n minus 2 part represents the case number minus the number of faces, subtracting the 2 top and bottom faces, the 2 left and right faces, the 2 back and front faces. Right, so even though I've got n minus 2 in these 3 different expressions, n, while constant in terms of the variable representing the case number, the 2's are all different. This 2 here represents the corners or vertices. This 2 here represents the edges. This 2 here represents the faces. So while we can use algebra in order to create the correct models, we're going to have to rely on our geometric shapes, these 3D solids and the visuals, to make sense of the expressions. So those are the things that I need you to really pay attention to. Now, earlier I stated that you have the opportunity to win a prize. And so the thing that I want you to really focus your attention on now is recalling or writing down these models that we see here. And I want you to think about how you can use these models to answer the question that I have posed in a second. So what MCPSS is doing for those tuning in this week, including tomorrow, is that you have the opportunity to win a prize from Chick-fil-A or the county. And the way to win that prize is to submit a correct answer to the question that I pose. And so here is your chance to win. The problem that I'm asking you to solve is this. If you were to paint the faces on a case 10 cube, so a 10 by 10 by 10 cube, how many of those smaller unit cubes, so these smaller cubes, how many of them would have 3 faces painted? How many would have 2 faces painted? 1 face painted, and then 0 faces painted? Think about the expressions that we came up with, the equations that we were able to use to model. And if you didn't get a chance to write those down, think geometrically and visually about where these things are located. Where the 3 faces painted cubes are located, where the 2 faces painted are located. Along the corners, along the edges, along the center face of the larger cube itself, within the inner part of the larger cube itself. And so now that you've had a chance to record all of this and think about the answer, once you have it solved, you're going to email your response to mcpsstv@mcpss.com. And they're going to review your answer, and if it is correct, you will have the opportunity to win one of those prizes. That's all that we have for today. It's been my pleasure to present these lessons to you the last several weeks. I hope you all have a great summer.